Assalamualaikum and a very good day. So we continue with chapter 10. The subchapter for chapter 10 will be cleaning and disinfection, cleaning in place CIP, cleaning out of place COP, and lastly effectiveness of disinfectants and sanitizers. Okay, what is cleaning in place? CIP. So it is actually cleaning inside equipment. So if you look at these two diagrams here, let's concentrate on this first diagram. So you have a process vessel, it's like a pot where you cook your food material here. So there will be a cleaning system that's built in to clean up the process vessel. So you don't have to go into the process vessel and do the scrubbing, but the machine will do it. Yeah. So in this in situ cleaning, so you're gonna have system with a tank of detergent, and you have water will come in, and there will be a mixing here. Okay, a mixing between different ratio of water and detergent, and this mixed water and detergent will be pumped by a CIP pump into the process vessel. Yeah, and then sometimes the dirty water will be flushed out of the system. Yeah, and then sometime after flushing out, so the detergent with water, soapy water, it still can be usable, so it can be recycled into the system and then reused again. Okay, the next diagram where you have the reactor. Okay, this reactor is the process vessel. And then you have the CIP skid where you put in the cleaner or detergent water inside this CIP skid, and this will be pumped into the reactor and then will be sprayed. Yeah, so inside this reactor will be sprayed, and then all the dirts will be cleaned. You're gonna have liquid charge, nitrogen or compressed air, all this to dry up the internal of the reactor, and all this will be pumped out, either pumped away from the system or being recycled. Okay, this diagram shows the fluid motion in a dead space. So if you have a piping system, okay, you have the main pipe, and then you have this dead area, another pipe going up from the main pipe. So if you push fluid into liquid into this pipe, so some of it will go into this dead area, but if you increase the length of this dead area, so the liquid will not be in turbulent, will not move inside this dead area. Yeah, so this graph shows the velocity against dead area depth. Depth means the length of this dead area. So if you increase the velocity, so you can have if you increase the velocity, meaning that the turbulent condition in this dead area will be increased as well. Okay, for CIP, you need to understand the cleaning parameters. There are 4 cleaning parameters that are independent of the installation, which is ZRFT. 4 cleaning parameters. R stands for the detergent, Z stands for the cleaning time, and F stands for fluid mechanics, and lastly the temperature. T stands for the temperature. Yeah, Z is the cleaning time, R the detergent, the type of detergent. F is the fluid mechanics, the speed of the fluid, of the liquid, and T is the temperature. So you need to remember this ZRFT, yeah, the 4 cleaning parameters. So one of the first factor is detergent. What is detergent? So effectiveness of detergent is being affected by the chemical activity, composition, concentration, surface tension, and dispersing power. What is chemical activity is how the chemistry of the detergent react with the dirt. Yeah, chemical activity is how will the detergent dissolve the dirt inside the equipment. Reaction of the detergent with the dirt inside the equipment. Okay. Now, if you look at the this water droplet, so you can see that it's not being wetted onto the surface. So you need to put in the detergent, and then the droplet will be wetted and dispersed onto the surface. So one of the important aspect about detergent and water as well as dirt is the emulsion. Emulsion is the mixing. You look at this picture, you have oil and then you have water. If you shake this test tube, then still the oil will not be dispersed into the water. But if you put the detergent material or chemical, if you shake this tube, then oil will be emulsified into water. Then you have this white color substance or mixing. So oil and water are immiscible liquids. The two layers can be seen in the test tube on the left. Soaps and detergent are emulsifying agent with an affinity or the chemical activity for both polar molecule and non-polar oils. The effect of adding detergent to an oil and water mixture can be seen in the image of the far right like this. So the detergent must dissolve rapidly and completely in water. The detergent itself must be able to be dissolved rapidly, quickly. Must act quickly on the soil, so the chemical activity must be strong enough to act quickly on the soil or deposit it is expected to remove, such as protein, fat, scale. Scale ni benda yang melekat pada permukaan, ya. Scale, resins, burn, yeast, trap and pulp. Semua ni adalah the dirts on the equipment of food processing. High soil carrying capacity can be easy to flush off with water. So another requirement for detergent is high soil carrying capacity and should be easily flushed off from the equipment. Detergent should not foam and should be compatible with other material used in the plant or factory. So detergent must not create foam. Foam ni buih-buih, ya. Kalau kita beli sabun untuk basuh baju pun, kalau kita guna mesin basuh yang muat depan misalnya, so kita kena beli certain detergent yang tidak akan berbuih. Sebab bila berbuih foam ni, so the dirt will be separated and then will be will be transferred from another surface to another surface. Yeah, so it's not being dissolved inside the solution, inside the emulsion. And then the detergent also must be compatible with other material. If the material is made of plastic, for example, so detergent must not be corrosive and causing damage to the equipment. Cleaning detergent must have a conductivity well above that of water, and demonstrate a linear relation between concentration and conductivity. meaning that you can measure conductivity. If you put in detergent, the conductivity will be very much different of a pure water, because you are going to use equipment for analyzing the conductivity of water to know the concentration of detergent in water. Okay, for example, if you don't have the anti-foam agent in your detergent, so the foam will come out of the laundry machine like this, washing machine like this. So you don't want this to happen. So you don't want to have foams like this. If you have foams, then the dirt will be separated from the mixing or the emulsion, and then it will not be taken out from the equipment, from the food processor. Cleaning time, total duration of the cleaning process, and is the definition of cleaning time, and it must be sufficient to allow for the dissolution of soil, swelling of soil, saponification, dispersion, and final rinsing. So these are the process inside the equipment. Dissolution, soil is being dissolved. Swelling of soil, soil is being enlarged. Swelling this if it's in solid condition. Saponification is being extracted into the solution. Dispersion, dispersed into the solution, and then there will be final rinsing to cleanse off the detergent from the surface of equipment. The last residual layer of the deposit on the surface can only be attacked by a detergent if it is allowed long enough to react, with the reaction time being the time the detergent is in contact with the deposit at the right concentration and the right temperature. Sometimes you have to clean your surface using higher temperature. Joy is one of the most popular detergent used even at home to clean up your dish. A little bit expensive but very effective. Phases of the cleaning operation. Number one, the first is you have to do the pre-rinsing. If you go and do the car washing, for example, you know that the car will be sprayed with normal water first. So the objective is to lose components, and it will be flushed out. The main wash which must be checked at critical point, for example, heat exchanger, plates, pipe, bands, and tanks, and then internals of the equipment. This picture is an example of heat exchanger, and it is being used for pasteurization of milk. So need to flow in pure water first, plain water first, before doing the cleaning with detergent. This is another example of heat exchanger. This is this type of plate heat exchanger. This is shell and tube heat exchanger. All these are also an equipment for food processing. And then the next step is the intermediate rinse. The solution being flushed out is checked for neutrality, how much dirt's inside the solution. And then last is the final rinse, where the solution being flushed out and is checked to make sure there are no traces of the characteristic components of the previous solution. So there is no traces of detergent chemical. Okay, what it means by fluid mechanics? Fluid mechanics influence the flow of the detergent through the system. So we required turbulent flow resulting from friction where fluid is in contact with surface, and it is characterized by a number called Reynolds number, yeah, Re, and Reynolds number is 10,000 for smooth round pipe at the boundary layer with the surface. How do we calculate the Reynolds number? We call it as Newtonian fluid Reynolds number. Re equals to rho Vd over mu. Rho is density of the fluid, V is the velocity, fluid velocity, D is the pipe diameter, and mu is the fluid dynamic viscosity. You don't need to understand this equation, but this is what it means by fluid mechanics of the solution. So flow velocity during pipe cleaning should be around 2 meters per second. Minimum is 1.5 meters per second. If the flow velocity is too high, this will cause a pressure drop in pipe system and cause the system to be unstable, then can cause leakage. System should not incorporate pipes of several different diameters because the resultant flow velocity will be too low or too high. So the diameter must be the same. If different pipe diameters cannot be avoided, they should be limited to a maximum of 2 different sizes only. And then it is also important to avoid separating the pipe path into parallel stream, that because it will undefined flow and contamination. So pipe must be in series rather than in parallel. Temperature influences the cleaning temperature. This is another factor or parameter. The temperature influences the effectiveness of the detergent, and the optimum temperature of CIP is determined by the cleaning task and the detergent used. Yeah, for example, washing machine actually have different temperatures. For expensive washing machine, you can clean the cloth at higher temperature. Pre-rinse step above 40 degrees Celsius are not recommended because soil containing protein or starch will undergo chemical changes at these temperatures and thus impede or causing the washing to be more difficult. Yeah, so the pre-rinse step must be at lower or room temperature. You don't want the protein and starch to go chemical change, become solid and stick to the surface of the equipment. Table 27.1, typical temperature ranges for detergent. Yeah, so these are the example of 2 detergent: acid, which is nitric acid, HNO3, and then caustic, which is natrium hydroxide or sodium hydroxide. So for acid, the temperature is 60 to 65. This is to clean up milk, tanks, pipes, etc. The caustic soda, NaOH, it can be used at lower temperature or different temperature with different cleaning task. Fermentation task can be cleaned at low cold temperature. For milk, have to clean up at higher temperature, 50 to 80. The brew houses, milk pasteurizer with a lot of proteins, so you have to do it at higher temperature, 70 to 90, and 90 to 130 is used for UHT, ultra high temperature plants for milk or for juices, sterilizers for puddings and desserts. This is to kill up the bacteria. Disinfection. What is this disinfection? It must be a separate cleaning step, meaning that after the cleaning, then only you can do the disinfection, and must only be carried out after cleaning because soil residues can protect microorganisms. So you have to clean up the surfaces and make sure that the surface is clean. Only then you can do the disinfection. The strength of the disinfectant can be affected by the decomposition of soil, and bacteria that survive owing to insufficient disinfection can multiply in soil residues and contaminate the product. Lower soil concentrations permit the use of combined cleaning and disinfection agents. Yes, you can combine cleaning and disinfection agents, but only for low soil concentrations. If you can know the bacteria that can survive on higher temperature, we call it as high temperature bacteria, or psychotropic or thermolabile bacteria. Yeah, and then sometimes bacteria produce this biofilm, so it needs higher temperature and more a stronger detergent to clean up the biofilm. Thermal disinfection. So the parameter is temperature and time. Thermal disinfection kills bacteria but does not remove them from the sterile soil when it is formed. You can kill the bacteria, but the dirt is still there. So method of thermal disinfection include hot water, preferably direct flow through equipment and pipes, steam at a temperature between 70 and 80 degrees Celsius, maintained for 15 minutes. For production plant with a large volume such as tanks and hot pressurized water, spores of some bacteria and some mold fungi are killed only if the temperature is at 130 to 140 degrees Celsius. So to kill up the spores, so you need to know what kind of bacteria and fungi that will be infected or contaminate your equipment. So if spores are infected, then you have to use higher temperature of above 130 for 140 degrees Celsius for at least 20 minutes. It is important to prevent the intake of contaminated air during the cooling phase after thermal disinfection. So the equipment, you must avoid the external air from entering the equipment, or if it's need to be entering the equipment so that the pressure will be kept at a safety level, then you have to filter the air so that bacteria will not enter the equipment. Chemical disinfection depends on concentration, temperature, reaction time, and soil load. What is a normal chemical they use for disinfection? Even for COVID-19 coronavirus, usually it is natrium hydroxide. So activated chlorine decomposes rapidly with increasing temperature and therefore can only be used for cold water without collection. It cannot be used for standing disinfection because of its corrosive effect on stainless steel. So activated chlorine cannot be used for stainless steel. Peroxide compounds such as hydroxygen peroxide, peracetic acid, and also suitable as additive to acid cleaning solution. Peracetic acid can be used as a cold disinfectant at low temperatures. Iodophores have good bactericidal and sporicidal effects, can kill the spore of bacteria, but there are problems with flushing them out and the risk of reaction with plastic parts or corrosion effects. They are not suitable for temperature above 40 degrees Celsius here for iodophores. Quaternary ammonia have good wetting properties and surface activity. The disadvantage is that residue formation and strong tendency to foaming. They are rarely used in CIP or cleaning place processes. Halo acids, yeah. have comprehensive biological effects and are used in combination with acid carriers, completely free of foam and have good flushing properties. So alpha halo acid, this is a chemical. Aliphatic carboxylic acid react with bromine or chlorine in the presence of phosphorus or a phosphorus halide to give alpha halo acids. These are the reaction. You have aliphatic carboxylic acid. You react with chlorine or phosphorus, and then you have the alpha halo acids. Alpha mean the first carbon of the molecule. So you have alpha halo acid. If you react with bromine, you have alpha bromobutanic acid. Okay, this figure 27.3 is the state-of-the-art hygiene design compared with standard design. So this diagram shows the standard design, and the top diagram shows the state-of-the-art design. Yeah, and then you have the inline access unit. So this figure shows a pocket-free design. So this one is the pocket-free design for process pipelines, and all integrated component in a functional system described as a hygienic design. So the top diagram is hygienic design compared to the bottom diagram. By comparison with the standard installation, the hygienic design reduces cleaning time significantly, which means that production time can be extended. Type of CIP system. You have several type of cleaning in place system. Number one is single path CIP system. In this system, a freshly made up cleaning solution is supplied to the plant and then drained out. No residual circulation in the cleaning system. The single pass system is used when there is a high degree of soiling, and appropriate when it is critical to prevent cross-contamination. You don't want any cross-contamination, so you're going to use single path CIP system. This system is commonly used in the pharmaceutical industry. This is the diagram of a single pass CIP system. You have detergent, water will be mixed, and then this solution will be pumped by CIP pump onto the top of the process vessel, and then you have a spurger here, the sprinkler, so it will be sprayed onto the surface of this vessel, and then the liquid will be eventually drained off from the system. So single-use CIP system, you have single path and then single-use CIP system. A freshly made up cleaning solution is supplied to the plant, circulated and then drained. There is a circulation. This system is used when there is a high degree of soiling or when cross-contamination must be avoided and the volume of cleaning solution in the system is low. And then you have a single-use system. This is the third system. CIP solution is used once and then discarded to drain, used to prevent microbiological cross-contamination, and then it is high cost for cleaning chemicals, water and water disposal. Okay, this is one example of basic single-use system. Okay, basic single-use system. You have the CIP written line. This is a conductivity meter, and then you have a flow meter to control the process. and then it will go to and then it will be mixed with water, and then you're gonna have this buffer tank containing the solution, and then the solution will be pumped. So you have the CIP supply pump. All these are the symbol for engineering. Yeah, symbol for pump is like this. Yeah, symbol for analysis equipment is like this: conductivity and flow. And then this pump will pump in the solution, mix solution of water, and you going. Oh, this is CIP buffer tank, yeah, together with cleaning chemicals. And then in the line, you're going to introduce caustic, acid, or sterilants or disinfectant inside the line, yeah. And then you're gonna have temperature controller system, yeah, CIP heater, where the cleaning mixture is heated. This is heat exchanger. Steam is going to be used to heat the solution, and then you're going to flow into the food processing equipment or the vessel. Yeah, so you have a flow meter, you have a temperature thermometer, temperature indicator, and you have the conductivity meter. So the chemical must be able to be used with conductivity meter, must produce measurement or values of conductivity. So you're going to have the CIP supply, and then this CIP will be used to clean up the vessel. Another system is the recovery CIP system. This system allows for multiple use of the concentrated cleaning solution. Why we want to use multiple? Because the cleaning solution is expensive. It can encompass several cleaning tasks carried out simultaneously. Cleaning solution is stored after circulation. There are large circulation volumes in the cleaning system, and the cleaning plant is installed centrally. So you have a central cleaning plant, and then you're going to distribute the cleaning solution to different processing equipment.